Okay, welcome everyone. We are recording this meeting just so you are all aware. But welcome. We're just gonna wait a couple minutes to see if anyone else joins us. And please continue to let us know where you're joining us from. Say hello in the chat. And for anyone needing Spanish interpretation, if you go to the bottom of the screen, there should be a button in the globe symbol that says interpretation, and there's the option for Spanish interpretation if you click there. If anyone's having any trouble with the translation or any other technical difficulties, just let us know in the chat and me or Jason will try to help figure that out. Okay, with that, I think we're 1 minute past the hour. So I want to welcome everyone to our very first event. We are the Member Connectivity Subgroup, a brand new subgroup of the Western Hemisphere Shorebird group. And the goal is really for us to make these events to bring the group together between our biennial conferences. So we're hoping to get together for several of these events. We have a couple planned this year and next. And we also have a Discord channel where we want to create more of an informal space to chat and talk about ideas and learn what kind of events you'd like us to host in the future. So with that, I have the pleasure of introducing our inaugural speaker, Dr. Antonio Cantú. Dr. Antonio Cantú is assistant professor at Sul Ross State University, and he is an expert in remote sensing and community ecology, specifically with wetlands and intertidal systems. So we thought he would be the perfect speaker for our first event, and we're really excited to hear how he can tell us about how all the capabilities Google Earth Engine has for ecological applications. So with that, I'll hand it over to Antonio. Thank you so much.
Hey everyone, thank you Tara for the introduction and for the invitation, as well as Jason and Kirsty. Really happy to be here. I'm going to try and share my screen now. Hope that works. All right, can you all see that?
Yes, we can.
Awesome. All right, let me get started then. So yes, again, thank you for the invitation. The idea here was to kind of give a broad overview of Google Earth Engine, which is a tool that's been trending among ecologists and worldwide for spatial analysis and more broad scale spatial tasks in general. This is a tool that's been around for a decade or so since it first started, but it's been developing super quick and more widely applied. All of you probably at some point have run across a web app or some tool, geospatial tool that has Google Earth Engine behind it, running it. So let me just give a quick overview of Earth Engine, and then I'm going to talk about a case study on how I've been applying it for ecological questions, and also kind of focus on the workflow on how this works and how you can get started. First of all, Earth Engine, it's a cloud-based geospatial analysis platform run by Google, as you might have expected. Some of the key features of Earth Engine is that it provides thousands and thousands of data sets that contain ready-to-use satellite imagery and other geospatial data in general that you can just simply pull and use for any type of analysis. It is cloud-based processing, meaning that everything that you run in it, it's not really happening in your computer. It's actually going to the cloud, to Google's servers, and everything is being processed there, and you just get results back immediately for you to visualize and analyze in real time. One big thing that it's mostly used for is to track changes, environmental changes over time. So when you go into Earth Engine, if you just, all you need is a Google account, right? A Gmail, essentially, to sign up. It's free. And once you sign up, you're an Earth Engine user. You go to code.earthengine.google.com, and this is the screen that you see. This is the code editor. It's by default how Earth Engine was built. So one of the key features of it is that there's a large public data catalog in it. And all you have to do once you're in it is go to this search bar up here and type pretty much any spatial data set that you know. For example, if you go ahead and type Landsat in there, you're going to get a list of all the available Landsat imagery that you can use, Landsat 5, 7, 8, 9, or you type Sentinel and you get all the imagery that they have. So traditionally, one of the things that took a lot of computational power and also space was downloading satellite images, which are just huge rasters that take up a lot of space. It takes a while to download and a while to process as well. One benefit of Earth Engine is that you just type it in here and pull it, and it's boom, it's right there, ready for you to use. So that's where you start. You search any data set that you're interested in, or multiple. You can use as many as you want at the same time. Then the code editor has these four main panels. In the top left, you're going to see these three tabs. One of them says scripts. That's where you save all the code that you develop. And you can, arrange by folders or pull existing scripts that you find online or that someone shares with you, and that's where you're going to see them. Then you have Docs tab. That's documentation. So any information on Earth Engine, it's going to be found in there, like all the functions that you use. For example, here in the middle panel, you see in purple EE.image collection. That's a function, Earth Engine specifically function. So you go to Docs, you look it up, and it tells you what it is, how to use it, etc. The idea is to have all the resources you need to apply it ready for you here to help you. And then the third tab in there, it's called Assets. Assets is where you save things that you bring into Earth Engine. For example, polygons, shape files that you just want to import and analyze something in a given area. That's where you're going to see it. Or if you already have existing rasters that you further want to manipulate or use for a different analysis, that's where you're going to find them in your assets. Then you have this middle panel, top middle. That's your main code editor. Earth Engine by default was built in JavaScript programming language. So the code editor here is in JavaScript, but you can also use it in Python or R. Not in this development environment that you see here in the screenshot, but actually, for example, Python, you can run it in Google Colab or in and Jupyter and R, well, RStudio. In this panel, this is where you write all your code, where you see imports. That's where you can bring in your assets, for example, your polygons. And then you see a few tabs on top where I want to highlight the one that says get link. And in Earth Engine, as you write code and you feel like you want to, have somebody else to collaborate or give you input or feedback on your code, you just hit the get link button. You get a link, you send it to that person, and they see exactly what you've been working on their side. So, and they can further, this is a really good way to collaborate. You write a piece of code, you send it over, then someone continues working on it, sends it back to you, and so on. So that's really handy and easy to do. Then on the bottom, you have your map. One really cool thing is that as you're writing your code, you can visualize things or write things. For example, you can draw polygons, put points on the map like I have in there. I have 2 points in there. You can directly do it on the map, and then that goes back to your imports in your code. So you can further write and develop code for that. You also have a layers panel that if I hit run on that code that I have next to the tab that says map up here, I don't know if you can see my mouse, there's a layers panel that opens up where you can inspect and visualize and just see what you're creating and working on as the ways to get feedback within your code. And then the last panel here on the top right, you have the inspector. So if you're familiarized with QGIS or ArcGIS, it works the same way, where you hit inspector, then you hit on the map, and you get information like metadata, pixel values, things like that help you further give you feedback as you're writing your code. The console is where when you run things, that's where you're going to see the progress, any errors associated with your code, all that type of information is going to be in your console. And then tasks, it's for harder tasks, like processes that needs to be done that where it requires you to go and hit run. For example, if you develop all this code, say you have a global data set where you just analyze all the areas that were burned in the world in 2021, and you want to export that map, well, that's going to be a huge file, right? So you got to go to task and manually hit run to export that to your local computer. Because it's Google, automatically it's going to be linked to the Google Cloud. So everything's going to go to the cloud first, and that's where it's going to be stored, unless you tell it that you want it, for example, in your local computer, because you don't have enough space in the cloud and so on. So that's just an overview of the code editor. How you use Earth Engine, it's a very simple workflow. First of all, you access the data, as I mentioned. You write the code, you process everything in the cloud. Again, you write the code, run it, it goes to Google servers, and it comes back. The results come back to you. You visualize and export. That's in broad terms, that's the way Earth Engine is used. Of course, when writing the code, that's where the real complexity is. Again, everything is happening remotely, which is a big advantage because it reduces hardware and storage constraints. And it's in having the map in there, it's also very handy because you get real-time feedback and you're always interacting with the map and sort of QA/QCing as you go, which is really handy. So just to give you a few examples of applications of Earth Engine, you can do land cover classification. That's one of the most common tasks that researchers or agencies do in Earth Engine. For example, using time series imagery to classify anything that you're interested in. I do it for wetlands, but you can also do forest, agriculture, or any land feature. Change detection as well, because you create time series of imagery. You can apply different spectral indices and track a specific change in something that you're interested in. For example, the normalized difference vegetation index. You can do hydrological modeling. That's one of the things I do the most in Earth Engine. The case study that I'm going to talk about specifically looks at tracking surface water changes over time. Climate analysis as well. You can track long-term changes in precipitation patterns, for example, or go into further analysis on how the frequency and intensity of droughts have changed. And of course, habitat mapping too. Like Tara here will be familiarized with developing habitat suitability models, for example. So Earth Engine is becoming the go-to tool for a lot of researchers and agencies and NGOs. It can really do anything spatial analysis that you need it to do. Of course, as everything, there's advantages and limitations. I've talked about mainly advantages so far. Just to reiterate a few, Earth Engine is free and open access. Again, there's that massive data catalog, which makes things super easy and fast to process. No local processing required. Again, everything goes to the cloud. In fact, I've run Earth Engine stuff from my phone, just opening a general browser in there and hitting run just for fun, and it works. So yes, I can tell you no local processing is required. And that makes it fast, and the map, the code editor makes it really easy to visualize and change things as you go, as needed. One thing I did not mention is that you can create web apps, graphic user interface friendly, where after you do your analysis and you get results, if you want to show that to the broader public, you can create a web app within Earth Engine and have people access the results that you developed. And another huge advantage is that there's lots of documentation and tutorials available, not only for the JavaScript based code editor, but also for Python and R as well. Within limitations, well, if you want to go straight into the JavaScript, there is a learning curve for coding, of course. Of course, that applies to R and Python as well. What I mentioned is that if you, for example, you're used to coding in R, you can do everything in R. You can access Earth Engine, visualize stuff, and on top of that, analyze, export and analyze stuff within R. So you can do everything in R if you want, or in Python. However, I would encourage people that are first coming into Earth Engine to try and learn the JavaScript version of it. That's where it was built originally, and there is a benefits to that. It's not as hard as it sounds. If you already know a programming language, learning another one is not as hard as the first one. I guess we can say internet requires a limitation. You do need internet access. There is limited ingestion. So for example, if you want to bring a raster that you created somewhere else, for example, a digital elevation model that can be something really complex and big that you created, but you want to use it in Earth Engine, importing that DEM to Earth Engine may take a while. and it can be a hard task. Usually Earth Engine is more made for you to use what's available than you coming in and importing something to then process again. There is another pipeline to importing data sets into Earth Engine. You got to communicate with their people, Earth Engine team, and they can do that for you to have it ready in their repository, in their catalog. And another thing is that really fine scale analysis are not ideal in Earth Engine. When I'm talking about the imagery that's available in there, like Sentinel, it's a 10-meter resolution. There's a few DEMs available that are 2-meter resolution in there. But below that, like if you're doing microtopography, for example, like LiDAR, sub-centimeter kind of scale things, that will be really hard to process in Earth Engine. Earth Engine is really made for more landscape level analysis than fine scale level stuff. So that's a limitation within Earth Engine. So how do you get started? Well, all you need is a Google account, a Gmail. You go to earthengine.google.com, you sign up, and that's it. You're ready. You're all set. Then you access the code editor by in that link, code.earthengine.google.com. And all you got to do is start coding, start exploring tutorials. There's a bunch of GitHub examples. But within that first link, there's a lot of documentation and guide through that you can just follow and get started. I encourage you to check out these web apps so that you can see just how much you can do in Earth Engine. These are all global analyses that have been done, such as the Global Mangrove Watch, intertidal flat change. These are huge. If you go to the first link again, in there's a few more examples that you can check. It's just something real cool just to see those and know that all of that can happen within Earth Engine. It's very fantastic. So I encourage you to check those out as well. So, all right, that's a broad overview of Earth Engine. I'm happy to, respond to any questions at the end regarding anything Earth Engine, if I know it. But now I want to focus on a case study on how I've been using it, for ecological research. So this project, Mapping Wetland Habitat Availability in the Chihuahuan Desert, began as a collaboration with Patrick Donnelly from Now Ducks Unlimited in Inc., who also works with closely with the University of Montana. He was the one that taught me how to use Earth Engine in the first place. And what we were interested in was, we know there's a lot of wetland issues worldwide where water use and climate change have been affecting habitat availability for migratory birds. But very little is known about the Chihuahuan Desert. So we were wondering, how is wetland habitat specifically changing in the Chihuahuan Desert? Chihuahuan Desert is North America's largest desert, and also one of the most unknown relative to other arid ecosystems. Within the Chihuahuan Desert, there's a network of wetland habitats. Most of them occur as closed basins and the rake basins, meaning those wetlands are the terminal lake, the terminal recipients of all the water that falls in the watershed. Most of the water comes in the form of rainfall during the summer monsoons. Very few of these are influenced by snow, only a few in the northern part of this map. has no influence, but most of them will. The main thing is rain. Rain in arid systems is kind of rare, so their hydro period is mainly seasonal, temporal, or episodic. If we look at the water balance of these systems, we see that evapotranspiration is the big driver of their water balance. Most of the water just outflows from the system as evapotranspiration, with very limited precipitation and runoff. Some systems are highly influenced by groundwater as well, either by recharge or discharge, but evapotranspiration is the main driver of these systems. But most importantly, these dots in this map provide a crucial stopover and wintering habitat for migratory birds. As you all know, those species that are breeding in northern latitudes in Canada, in Alaska, eventually migrate to southern latitudes, and they're all crossing these huge arid systems, these huge deserts, and finding those dots with water in the landscape can be crucial for their survival. This work was mainly driven by waterfowl. That was the main motivation to it, wetland habitat for waterfowl. So this graph shows waterfowl numbers wintering in the northern highlands of Mexico between 1947, 48, and 2006. This is data that came from the U.S. Fish and Wildlife Mexican winter surveys that they stopped conducting in 2006. And something you see here is that waterfowl numbers fluctuate over time. This is a very common pattern in arid systems because species are responding to habitat availability, meaning water is primarily the presence of surface water in the landscape. So as you see, if there's little water, a few birds will be in there, but when conditions are ideal, this region can support up to 1.6 million birds at a given time. So they can be really important when it comes to continental populations. The problem is that water use and land conversion, climate change worldwide is changing the water balance of arid systems. That's a global trend. In the graph in the right shows the Murray-Darling Basin of Australia in the top and the Colorado River Basin in the bottom. In light blue, you see the volume of water available in that watershed over time in the axis. And in dark blue, you see how water use, and that's human consumptive water use, has increased in both of these systems over the years. The most critical being in this case, the Colorado River, where now more water is used than what's available within the watershed. So this is a huge concern to wetland habitats. And this is the pattern, the trend that we see globally. So we hypothesize that all these issues are potentially, well, we know they're present within the Chihuahuan Desert, and it's potentially putting waterbird habitats in risk. But the truth is that very little is known about the status and trends of Chihuahuan Desert wetlands. However, a recent study by Patrick Donnelly showed that these systems in the Chihuahuan Desert may be showing signs of resilience, meaning that when they analyze surface water change in lakes and wetlands, as you see in lakes in panel A and wetlands in panel B, they found that, for example, compared to the Great Basin wetlands, there's huge significant declines in wetland area. Whereas in the Chihuahuan Desert, there seems to be more consistent or stable conditions, if not even increasing water conditions in the Chihuahuan Desert as depicted by the blue bubbles here. So the objective of this study was to determine long-term surface water dynamics and trends among these important wintering waterbird habitats in the Chihuahuan Desert. We specifically look at the periodicity of wet and dry cycles within the region, and also evaluate how the different climate variables may be explaining those changes that we see in surface water area availability. To do so, of course, we thought Earth Engine might be the best approach to answer these questions that we had. So we focused on reconstructing long-term seasonal surface water area for each wetland that we identify in the Chihuahuan Desert. Now, these are not the red dots that you see in the map are not all the wetlands that you find in the Chihuahuan Desert. These are simply the most important 2 waterfowl that we identified based on the surveys that I showed. So our general workflow here was importing these wetland polygons and their watersheds to Earth Engine to analyze surface water availability and then export the results. So let me explain a little more detail on what happened within Earth Engine, the Earth Engine workflow. First, we took 35 years of Landsat imagery from Landsat 5, 7, and 8. So you develop some code to make those 3 compatible so that you can use them all at once. Because if you're familiarized with Landsat imagery, Landsat 5, the bands differ from Landsat 7 and 8, so you got to do some manipulation there to make them all compatible in terms of the bands you can use. We imported our wetland polygons and applied this collection of imagery to those wetland polygons. But of course, one key of using satellite imagery is that you need images that are actually usable. So that means that you got to get rid of images or sections of images that have clouds and other features that like shade that you cannot use for your analysis. So we filter those areas with that contain cloud shades and other stuff to make a collection of images that we can use. We also filter to dates that were important to us. So this study only looks at the season from October to March of each year, because that's when migration and wintering is happening. So that was the first step, just getting our data set of imagery ready for analysis. Then we applied several spectral indices, like the normalized difference water index and vegetation index, to classify water in the landscape. And to do so, we applied this classifier called the spectral mixture analysis, which is a machine learning based classifier. Then we create time series of water. So for each season or each year, we mapped how much surface water there was in the landscape. We visualize this, review it, and we also conduct some analysis like regression and trends analysis. And of course, we're visualizing and getting feedback as we go. And then once we have the final product, we export that as a time series of annual surface water availability for each wetland in the Chihuahuan Desert. And then we repeat this process for climate variables. So instead of looking at the wetland polygon, we imported watershed polygons. Actually, we did not import it. We used a a data set that's already available in Earth Engine that's called hydrosheds, developed by WWF. So we just imported the watershed of each wetland and then imported another data set that's called TerraClimate, which provides monthly climate variables. And that's a data set that goes back to the, I want to say 20s or 30s, 1920s or 30s. So you have monthly climate information since that time up to this time. So we repeated the whole process and exported a time series of precipitation, runoff, evapotranspiration, and drought within each wetlands watershed. We exported those time series, and then I brought that into R for analysis. And specifically, I used star just to make pretty graphs, hydrographs. I also ran a man-Kendall trend analysis, which you can think of it as the non-parametric analog of linear regression. I applied Fourier analysis to see to assess the frequency and periodicity of surface water in the landscape, and also a random forest regression to see how different climate variables may explain surface water change in each wetland. Now, I'm going to mention that this is not the best way to do it, going to Earth Engine and then exporting and then bringing it into R and then analyzing. I could do everything within R. Just communicate with Earth Engine. There's a package library called RG, and that's how you communicate with Earth Engine in R. And you can do everything in there. Or I can do everything in Python too. So just FYI, there's that way of doing things as well, which is probably best practices. All right, results. So these graphs, this is a graph for each wetland. We have surface water area in hectares in the y-axis and time in the x-axis. And the first thing you see here is that there's high variability in surface water area within and among individual sites. But we do see some areas that are decreasing, that their trend, they're losing water over time. We see some areas that are increasing, getting wetter every year, and areas that remain constant over time, that doesn't have or show much change over time. However, if we look at everything together from a regional perspective, we find that water, surface water area has actually slightly increased over the whole observed period over these 35 years, as given by the tau statistic there, which you can think of it as a correlation that goes -1 with extreme decline to 1. So 0.14 is actually a positive. There's a slight increase in surface water over this time. Here's another way of looking at it. We have all the different wetland sites in the y-axis and time in the x-axis. The size of the bubble is surface water area, and the coloring indicates the trend. If it's red, it means that they're decreasing, blue increasing, and yellow, there's no change. So the first thing, and here they're ordered in a latitude, so northern latitude to lower latitude. And the first thing we see is that the wetlands in the northern latitude of the Chihuahuan Desert are more likely to be decreasing. So there's more red on top than there is on the bottom. That's what I'm trying to say. Another thing that we can see is that periodicity was mixed, meaning that at no given time, all wetlands do not follow the same wet-dry cycle. All of them are varying in in wet-dry cycles that range from 2 to 12 years, meaning that at a given year, some of the wetlands will be dry, but others will be wet. And then the next year, they switch. Those that were dry are now wet, and those that were wet are now dry. And what that's saying is that at any given year, there's some water in the landscape somewhere, which is great news for habitat. However, we did identify 3 major events when there were dry conditions across the whole region. And that was in 1989, in 2002, and 2012. Those were the only 3 big major events that were consistent across the whole region. And when we look at global climate patterns, such as El Nino, La Nina, Southern Oscillation, we see that those 3 events follow a strong La Nina event, that they happen during or just after a strong La Nina event. So this graph just shows the MEI, the multivariate ENSO index over time, which is based on ocean temperatures and in the Pacific equator. And that's what's used to determine when El Nino, La Nina conditions are happening. But this was the only real pattern that we found across our region. When we look at the climate variables that we analyzed, we found that evapotranspiration was the variable that best explains surface water area change across the whole region. And that's great news, because if we remember from the water balance, evapotranspiration is the main driver of arid wetland surface water. So seeing this variable being the most important indicates that for the most part, these systems are still behaving in a natural way. More things that I want to show you that you can do in Earth Engines, not just get a regional large-scale perspective, but you can also inspect individual sites specifically. For example, here we're looking at one site. This is Santiaguillo Lagoon in the state of Durango in Mexico. This is a 28,000 hectare wetland that we divided for the purpose of analysis into 2, a northern and a southern lagoon, because right here in the middle, the government back in the 80s constructed a levee road that disconnected the northern part of the lagoon with the southern part. They did included culverts and other water control structures to allow flows to go from north to south. But the locals saw that as an opportunity to dam the upper part of it to provide fisheries opportunities. So this resulted in 2 hydrologically distinct sites and that's why we treat them as separately here, with one having a positive trend, the upper side, of course, that was the whole intention of it, and the southern one with not much change and experiencing dry conditions every other year. These are our waterfall numbers that the state of Durango conducts. And here I just want to highlight that 2012 event is reflected in waterfowl numbers as well. Here's another site, another location we can see a lot in. This is Laguna Mexicanos in the state of Chihuahua, which has an increasing trend. It's getting wetter over time, and that's because it's being used as a reservoir for irrigation. But even though this area is increasing in surface water area, you can see in the map some red in there. In the map, the blue shows areas that are getting wetter. Red shows areas that are getting drier, and yellow is no change. But you can clearly see how this landowner here built a levee to dry this portion of the lagoon to grow something crop, likely corn. So even though this area is increasing, it doesn't mean it's doing good, right? We're still gotta look within the site to see what's going on, and this is another good way of detecting such issues. So some conclusions over the whole observed period. Wetlands in the Chihuahuan Desert show a slight increase in annual surface water area, which, if we look at from the continental perspective, this highlights that this area is still supporting habitat within the flyway, specifically the central flyway. However, at the individual scale, we still find many wetlands that are experiencing declines. From that bubble plot that I show you, we can tell that wetlands in the central and southern part of the Chihuahuan Desert may benefit more from more protection and management efforts, or maybe even worth to check on quality, more of the water quality situation in those, whereas those in the north may be needing more restoration because we show that there's more decline in surface water area at those sites. But again, this is a quantitative approach, right? So water habitat quantity is not equals quality. So that's another thing we have to take into consideration for a full assessment of habitat conditions. Evapotranspiration remains as the main climate driver, which is great news because it's suggesting that these areas are still behaving in a natural, at least from the hydrological perspective, in a natural manner. And finally, as other regions within the Central and Pacific flyways are experiencing water declines, wetland in the Chihuahuan Desert may play a larger role, providing habitat to migratory birds. Finally, just want to mention other ongoing future Earth Engine projects that I've been working on. One is developing satellite-derived bathymetry for mapping intertidal zones and applying these to foraging habitat availability models. That's something I moved away from the Earth Engine code editor, and I did everything in Python. And I'm also working on mapping soil erosion in the Trans-Pecos region of Texas, which is aimed at guiding riparian and grassland restoration. And that is an Earth Engine JavaScript workflow. With that, I want to thank you. Thank you again for the opportunity, and I'll be happy to answer any questions.
Thank you so much, Antonio. That was super interesting. Yeah, if anyone has questions, feel free to come off mute or put them in the chat.
And maybe while we give everyone some time to think or type their questions in the chat, I can start with an easy question. Or I guess, what would you recommend, Antonio, for someone who may be like really afraid of or intimidated by like the Google Earth Engine environment, or someone who doesn't have a lot of coding experience? Where's a good place to start? Where would you recommend?
I would actually start on their website, just navigating through the Earth Engine website. They really did a good job in providing videos, resources, examples. And I say this because even if you're not familiar with JavaScript, for example, they provide examples where everything you have to do is hit run, and it will happen. And then they make it very easy for you to go line by line and at your own pace kind of figure out what each line of code is doing and saying. So I will start there, and from there that will take you to another, their website will take you to another site, and that's where you're going to start your own journey in Earth Engine. But that's a good place to start, I think.
Thank you so much. And we also can share some resources. We're going to send an email out to all of the registrants with some of the resources that Antonio was talking about. Okay, we have a question from Diego Guevara. Have you found any issues discriminating water in areas where you have a mix of water and algae, or water that looks green can be confusing with NDVI and NDWI, especially if you have green areas nearby?
Yeah, not necessarily like algae or other things like that, but for example, turbidity caused a lot of issues. And that's why we end up using the spectral mixture analysis model, which is a classifier. So not only you use NDVI or NDWI, but you also inform the model on you have to train it on areas that, for example, if your issues to algae or areas that look green, you train the model to classify to detect those areas. So it's not just based on NDVI or NDWI. It's integrating multiple variables and actually running a classifier, if that makes sense.
Thank you.
And I should add to that and for example, water and DWI, you can use multiple indices for water, like the modified normalized difference water index, for example, and kind of use them jointly to make the best classification possibly. Yeah.
We have another question in the chat from Rick Langto. He says, I was wondering if you could comment on this temporal and spatial scale of water variables that you can download from the Google Earth engine. I ask this because migrating shorebirds can use very ephemeral, small wetlands. Can we track their availability in a reliable way?
Yeah. So for example, not in this case study, but the one I mentioned there, developing satellite-derived bathymetry for mapping intertidal zones. Well, intertidal zones are, those that are driven by lunar tides are undergoing wet and dry cycles daily, right? Not monthly, not weekly, but daily. So capturing that can be a challenge. And I think this applies more to the issue you're talking about. So the best thing you can do in those cases is have a lot of observations. One thing it's getting close. I'm not sure if we're there yet, but you can combine Landsat and Sentinel imagery in Earth Engine now. It's called the harmonized Sentinel, harmonized. Yeah, I think it's harmonized Sentinel Landsat dataset. But anyways, that's providing you satellite images every 2 to 3 days. So you get enough observations over a long period of time, and you can map those highly dynamic areas. So you get, every 2 3 days you map water, and then you're getting what the water conditions were at that site. You do time series analysis, and you can get you get enough variation so that you can have a full overview of the dynamics of that specific system.
Thank you so much, Antonio. And Rick did add another part to his question about if you think there's possibility to use Google Earth Engine to separate short and tall grassland areas, which is a perpetual problem for grassland shorebirds.
I do not know. I don't have much experience with grasslands. That's a good question, but I wonder if there's like a difference in, for example, NDVI that you can track, or maybe the proportion of bare soil or some indication that can't differentiate between the short and the tall grassland. But yeah, as long as there's some signature out there that you can track, a proxy or something, I'm sure you can do it.
Thank you. Yes, there's so many possibilities with Google Earth Engine. We have another question in the chat, but I'm not sure we have enough time to get to it. What do you think, Kirsty?
Just get to it quickly and
Okay.
yeah.
Yes.
Yeah.
Yes, there is.
So,
Yeah, you go ahead.
sorry. I wonder if these wetlands are experiencing sedimentation and if that increases evapotranspiration, which means less water storage.
There is. The second one that I showed in there, Laguna Mexicanos, that's the case in there. There's high erosion around it, as you probably saw the agricultural footprint around it. So sedimentation is certainly a concern in there. That can increase evapotranspiration for sure. But at least in that site, for example, that was not the trend that we observed. It was actually holding more water over time. I guess it depends on the soil type too.
Okay, thank you so much, Antonio, and thank you everyone for the questions. That was great. I'm going to share a quick slide as we get ready to leave. We thank you all for joining us today, and especially to Antonio for such an interesting and information-dense presentation. That was super great. I have a few announcements before folks leave. One is to join us on our Discord server. That's the Western Hemisphere Shorebird Group Discord server. It's new and a little bit experimental, but we have a few different channels for conversation, and we've been having a monthly journal group where we talk about recent shorebird literature. It's been very interesting. And if you're not familiar with Discord, it's similar to Slack, but it's a free platform. So it's helpful for us who don't have, there's no paywall. And we also want to say, if you're interested in helping us organize these webinars, feel free to reach out either through Discord or to my email, which you should have received with the Zoom link. We're really enthusiastically welcome anyone to help us. And Tara's also going to drop a quick post survey in the chat, and we'll follow up with that via email too. We'd really appreciate your feedback, especially as we get this webinar series going. And lastly, we have another webinar coming in mid-October. It will be a panel on feeding ecology of shorebirds. So look out for details on that. The date and time are to be announced. And we really appreciate you all being here. Thank you so much for joining, and we hope to see you next time. And thanks again to Antonio and to the executive committee of the Western Hemisphere Shorebird Group for supporting.
Thank you, everyone.
Thank you, everybody.